Hi, pre-calc students. We're on section 8.2. We're going to discuss three-dimensional equations. The solution to an equation with one variable is where you get a single number that satisfies the equation. The graph is a point on a one-dimensional graph. Basically, that means it's a point on a number line. In the last section, we worked about solutions with equations in two variables. It was an ordered pair that satisfies the equation, and the representation is a line. The graph is a line on a two-dimensional graph. Now, the solutions and equations in three variables that we're learning in this section is an ordered triple. That's what satisfies the equation. And the result, instead of being a line where two lines intersect or don't intersect or the same line, now the results are a plane in space. So it's a 3D type of solution. So the first thing here is we're going to plot a point 5, 3, 4. That's in the same order as your x and y, but there's a third variable of z. So the x-axis is the one coming out straight toward you. The y is horizontal, and then the z is up in the air to make it a three-dimensional graph. So the first thing you want to do is do the 5 coming out towards you. You can actually draw a box to create this picture. So you got 5 units in the x direction, and you can make a little point in that direction so that you can create one side of the box. The next one is going to be going in the y direction 3 units, so that's to the right by 3 units, and then the last one is going up by 4 units. Now, if we do all directional sense in all 3 of those directions, you're going to take it like a rectangular prism. The 4 units up goes in all of these directions, so you can take it to all these. All these are also going to be parallel, so you notice how this one's coming out diagonally in the x direction. It will as well up on the top of the box and the bottom of the box, to the right of the box, left of the box, all coming out diagonally. The red lines that go to the right are going to be on the top of the box. It's also going to be on the front of the box. They're all going to be 3 units long. And then where these 3 dimensions all come together, it's kind of like out in the space here. This point right here, make it a big black dot. This point right here is the coordinate of 5 units out toward you in the x direction, 3 units going to the right in the y direction, and 4 units going up in the z direction. So it's kind of, you got to draw that 3-dimensional box to see that placement in 3D. If we're solving a system and you're trying to find values to the solution, there's a lot of different answers for this system. It's any point that would make this statement true. So you can literally just make up some numbers. Like if I plug in 0 and 0 for the x and the y, those 2 terms are gone. The z would have to be equal to 6 in order to make that statement, the whole sentence, equal to 6. If maybe you make up the numbers 0 and 1 for the y coordinate, the first coordinate's gone. If y is plugged in as 1, that term right here is -2. Add it to the other side, the z would have to be 8 to make that statement true. You can do this with any combination, make up anything. Maybe if you do 1 and 0, that would make the first term 3, the second one's out of there, so 3 plus what is 6, that would be 3 for the z. So any combination that would make that sentence equal to 6 would be a point that works in that equation. The system to the 3 equations in 3 variables. Last section you did 2 equations with 2 variables. You had lines. This time the equation is going to be represented with planes. So a plane in space. So there's different ways that these planes can come together to create solutions. First one is it creates a unique solution, where the 3 planes come together and intersect at a single point. That's like this first picture where you have this point where they all cross. That point would be in the form of A, B, C, or X, Y, Z. The second type of solution you can get is they intersect in a line that's called linear dependent. So there's an infinite number of solutions all on that line where they cross, and it would be represented as a coordinate where you can plug in numbers that would make that statement true. So this line where they all come together, there's an infinite number of answers, all represented by each individual coordinate. On the third way, the planes can all intersect at all points, and that means that they're all basically sitting on top of each other. That would be a coincident dependence. That's represented by this third picture here, where basically all the points are in common for all three equations. Basically, it's the same equation kind of disguised with maybe a multiple of 2 to one of the equations or something like that. And the last one here, this looks like something that would have no solution because there's nothing that's common to all three planes or all three equations at the same time. So there would be no solution. It might work for 2 of the equations, but not the third. And that's it.